Okay. Good. Okay. So okay, I know I kind of told you something about this, but maybe it was not very clear. So I'm going to spend a little bit more time again uh, recalling this problem, this scenario, and I'll also do a little bit of some proofs to kind of justify my kind of physical intuition. Before that, let me just state the quantum covering lemma, and then uh, I'll just state this for completeness. So there are parts that I have left you to complete, but lemma. Okay, I'll state it very precisely. So suppose x ex sigma x is an ensemble with ensemble average rho equal to summation px of x sigma x for um, every eta greater than 0. So let's say there exists an n sufficiently large. There exists, let me say for all n, a collection with cardinality m satisfying 1 by n log capital M is less than equal to S of um, rho minus Px of x S of sigma x plus theta, such that the L1 distance, the trace distance trace distance rho tensor n minus 1 by capital M equal to 1 through capital M sigma xn of M is less than equal to eta. Okay. So just one point here. So suppose, I don't know whether I mentioned this, suppose theta can be written as this classical quantum ensemble, Px of x. So theta, let's say xy. So it has two uh, uh, components, a classical component coupled with a quantum component. So observe that I think I did this. Theta x is px of x bracket xx, get bracket xx, and theta y is rho. So then, so your really rate is 1 by n log capital M is less than equal to, I can say, S of y evaluated with respect to the quantum state theta. It's like saying h of py, right? It's really what I'm saying. I mean, theta xy is like pxy. So when I say h of py, that's really what I'm saying. Minus s of y given x theta, okay, plus theta. So this is the quantum covering lemma. I'll just give a minute for you, or give a few seconds for you to kind of be comfortable with it. Okay. Good. So what is okay? So just for completeness, I mean, it's trivial, but you should try and prove this. You should actually try and prove this without. It's a slightly simpler proof. So I'll state the classical analog also before I go further, and I will actually it will be of interest. So classical covering lemma. Suppose x comma y are finite sets and pxy is a PMF. With marginal py. For every eta, there exists in n. There exists for all n sufficiently large a collection I'm writing, it could repeat. That's why I'm writing. I should be writing it as a set, but because there may be repetitions, I don't want to write it that way. That's all. That's the only reason I'm doing that. A collection of cardinality at most cardinality M satisfying 1 by n log capital M is less than equal to I of x colon y plus eta, that is essentially h of y minus h of y given x plus eta, such that the marginal, sorry, this is the equivalent of the trace distance, right? So the total variation. The marginal can be simulated by just choosing each one of them uniformly at random. Okay, so that's the.
Sir, this is the mod distance, right? Like,
This is the total variation. This is the mod. The just mod of A is A if A is greater than equal to 0 or minus A equal yeah. Is the total variation. I mean, remember, say if I have two commuting operators, right? Rho minus rho and sigma, suppose they are commuting. Everything is commuting. So that means I can write it as u lambda u dagger minus u gamma u dagger. Suppose I do this. If I look at the trace distance, right? This will be actually summation lambda I minus gamma I, correct?
Yeah.
So that's exactly what it is, right? So essentially what is happening, the classical world, the entire classical world is sitting as a commuting inside one is all everything that we are doing in the classical world is commuting. So you can recover the classical world by just looking at one commuting collection u dagger. So essentially you're looking at commuting I wouldn't call it yeah, you can say it's a subspace. It's just everything is in one subspace spanned by the eigenvectors of ui. Does it make sense?
Yes, sir.
Yeah. Okay, great. Now I'll go into this quantum measurement compression. I'll explain this slightly better. See, now this is the question, right? So I'll so as we okay, so take a quantum state, you prepare a quantum state, and you give it some, a characterization rho. So you prepared a quantum state, you prepared a subatomic particle in state rho, or its behavior is characterized, is specified through this density operator rho. Okay, and you have a measurement. So when you make this measurement, so let's say the measurement has 0, 1, 2, 3, four outcomes. So when you make this measurement, so you, even if this is let's say even if this is a pure state, I mean you put all your effort and there's absolutely no mixture, but it is a pure state, and you have a general measurement, and you perform this measurement, you're going to get a random outcome, right? So can very simply take, if your lambda not, if these are just not aligned with p, then you are going to get a random outcome. Okay, now the question that really we want to ask, okay, so you put all your effort and you prepared your quantum state, and then you give it to somebody and he does a measurement and he gets a random outcome. Okay, so the question is, how much of this randomness is really something that is a function of the state, and how much of it is just pure randomness? Okay, so I will state this. So when a measurement is performed, even on a pure state, the outcome is random. So the question, the big question is, how much of this randomness is intrinsic to the state and how much of the randomness is extrinsic to the state. What is the guarantee that this measurement is not even looking at the state? What is the guarantee, right? That it is just throwing out something completely at random. How do I measure what amount of this randomness is really something I cannot avoid, and what amount of randomness is really due to some extrinsic factor? Okay, so in other words, so so I want to randomness in the outcome. I want to split it into two parts. Okay, so in some sense, I want to split it into two parts. So intrinsic to the state and extrinsic to the state. Okay. So okay, so then how do you kind of answer this question, right? How do you kind of answer this question? So the way I will try to answer, so the way so this problem is not easy to formulate. Okay, how do you kind of understand what is intrinsic to the state and what is you can't see this quantum state. You just go prepare something, you make this measurement, you get something random, and I want to know how much of this randomness is intrinsic to the state, how much of this randomness is out extrinsic. I don't know, it's not easy to measure, right? So one way to kind of see is, can we simulate the measurement process using an external source of randomness? Okay, so that is this. So can we simulate this measurement process via an external source of randomness? So more particularly, so look at what happens when you make this measurement, right? So when you make this measurement, your quantum state could go to one of four. Let me just say two, okay? Just for the sake convenience, I'll just say two. So it could go to either this state with a red value, red register value, or it can go to say this state with a blue register value. Let's say the probability of this is 0.3 and the probability of this is 0.7. See, you fix your rho. So rho is fixed. So your quantum state is fixed. You fix your measurement. So it is like, you fix your pencil and you fix your scale. And if you do the measurement, you're going to get random outcome, right? And the question is really, I mean, is this scale even looking at the pencil, or it is just throwing something random? That's the question you want to ask. So okay, so if so let's do the following. So we want to communicate the outcome of this measurement to some Bob, right? So we want to communicate the outcome of this measurement to Bob, and that his whatever he stores in his register has to be in relationship with the post measurement state. See, the idea is the following, right? So I know when I fix my quantum state and when I fix my measurement, I know that my probability of the outcome is, it's going to take the red value with probability 0.3, and it takes the blue value with probability 0.7. Now let's do one simple thing. Suppose Bob simply generates a random variable with distribution 0.3 and 0.7. Would you accept this to be the outcome of the measurement?
No.
Clear, right? So if he can just simulate, so he can simulate the statistics of the outcome, but you wouldn't accept that as the outcome of the measurement. Why?
Because if Alice gets the red thing at that time, he also has to get like that outcome.
See, that is a crucial point, right? So it is not that simply, so it could be, so one possibility is nature is not even like, bringing any relationship between the quantum state and the classical part. So it is just throwing out a random variable with probability 0.3 and 0.7, and this is in a completely different, it could be possible. This could be possible. If that is the case, clearly the outcome has no relationship to the quantum state. But suppose in reality what is happening, there is a relationship that is built between the the quantum state and the classical register. There is a relationship that's built between the post measurement quantum state and the post measurement classical register. See, what is nature doing? Nature, when you make this measurement, right, when you make this measurement, it is throwing this classical quantum state with probability 0.3, and it is throwing this classical quantum state with probability 0.7. That's all it is doing, right? And somehow your classical register is containing some information about the quantum state. Now, if I can simulate exactly this same post-measurement state, but without doing the measurement, right? I'm not going to do the measurement. I have this quantum state with me. Okay, I have this quantum state with me. I have this original measurement that I'm supposed to prepare, it's supposed to make. And I know if I make that measurement, I will end up with this ensemble. But suppose, don't worry, I'm not going to do that. I'm going to take this quantum state and I'm going to do some process on this that will end me up with the same statistics as this, exactly the same post measurement state. If I can create, then I've essentially simulated the measurement, or essentially my classical register now contains exactly the same amount of information about the quantum state as if I had done the original measurement. Do you agree with this? This is a key point. Questions or what? You're silent.
Yeah.
Like we have to use some random bits, right? Like as you said last time.
No, hold on. Do you agree with this? How we do it, let's not worry. What I'm saying is, when you make this measurement, what you end up with is this ensemble. So what is nature doing? Nature is very simple, right? You fix a row, you fix a measurement lambda, lambda 0 and lambda 1. What nature is doing, it's just completely random, right? You're going to get this post measurement state with probability 0.3, and you're going to get this post measurement state with probability 0.7. You agree?
Yeah.
Now, okay, I am now going to replicate this process. I'm not going to do the measurement, but I'm going to replicate this process. So that process, whenever I do it on the quantum state, I am going to get 0.3 probability the red classical quantum state, and I'm going to get with probability 0.7 the blue classical quantum state. Okay, so this is what is a simulated process. Okay, I'll call it a simulated process. I claim the following. I claim that the register, classical register in the simulated process, contains exactly the same amount of information about the quantum state as the classical register in the original measurement. This is the key point. So I don't know what is the information content. I don't know what is the information content of the original classical register. I don't know. I can't, I have no way of computing it. I don't know how much information does the classical register carry about the quantum state. I don't know how to answer that. But what I will do, I will create another process. And the other process will design the same ensemble for me by looking at the quantum state. If I can do this, then I claim whatever is the information content that this classical register contains about the quantum state, it is the same amount of information my classical register in the simulated process contains about the quantum state. I don't know what that value is, but that's what it is. Do you agree?
Yeah.
That is the key point. Okay, so this is really the key. I don't know what it is, but this is it. Now, how much?
Sorry, just one question.
Yeah.
So this means that the final state in the simulated thing should be theta 0 tensor 0 plus theta 1 tensor 1 with the weighted, right?
Yeah. I will write it
0
down.
is red.
So
Okay.
let's call this. Okay, let's call this gamma 0. I don't know, it's some state gamma 0. This is gamma 1. This classical register is in state 0 0, and this classical register is in state 1 1. So my original measurement, the original measurement is yielding this, right? 0.3 times gamma 0 tensor 0 0. I don't need the summation. Plus 0.7 times gamma 1 tensor 1 1. Do you agree?
Yeah.
I can compute all this because I have my rho with me. I have my lambda 0 and lambda 1 with me. These are all very well fixed. Give this to me. Take this, give this to me. I can compute this. I don't know how much information is the classical register carrying about the how much information about the quantum state ended up in my classical register. I don't know. But what I will do, I will simulate exactly the same post measurement quantum state. So in other words, it's like this, right? So there are two worlds. So one world, there is a quantum state rho. I will take some time to explain this so that the physics is clear. We can do the math a little later. So and then there is so in this left side world, somebody does a measurement, the original measurement. They have designed this. They have given this rho. They have given this lambda naught lambda 1. I mean, on the right world also we have the same thing, and out comes the red classical quantum state with probability 0.3, the blue with probability 0.7. On the right side world, I have the quantum state rho, but I'm going to do some weird process. I don't know what it is. I'm going to do some weird process. But I will end up with the same ensemble as the right-hand side. Now, there is no way to tell whether nature is on the left side world or the right side world. Do you agree? Because nature is also giving you out this, and I have nothing else to see. except that I can see my classical register on my side. On this side, I can see my blue register, classical register. That's really all I can see. And I have no way to see whether nature is really doing the left side or the right side. Do you agree?
Yeah.
Yeah.
Yeah. Now the question is, okay, what all do I need to simulate the right hand side? I know what the left world requires, right? Left world requires you have the quantum state, and you have this measurement, you do this measurement, you're ending up with this ensemble. On the right side, what all do I need to cook up this post measurement state? So I know there is randomness in the post measurement state, right? There is randomness, there is some 0.3 probability, something happens with problem 0.7, something else happens. So clearly I need some source of randomness. Okay. So I'm going to take two sources of random. I'm going to take two in some sense streams of randomness. Okay, one stream will come from the quantum state. So one stream of the randomness that I will get will come from the quantum state, and one stream will come completely independently of the quantum state. It's like completely independent, and I'm going to use these two to somehow simulate this post measurement state. Okay, and so the idea is the following. So broad. Okay, so now I'll go into a little bit more specifics, and I'll tell you what I do on the right hand side. See, I have this quantum state. If I simply perform measurement lambda naught lambda 1, right, then I'm going to get a register with probability 0.3 and 0.7. And if I have to communicate, so let's say, to now I'll just make this slightly different. Now what I'll do, Bob is okay, so let's say Bob is here, and Bob has the classical register with him. Alice is here. Alice has the quantum state with her. Now what I want to do, I will do some process here and extract some classical register. Okay, some classical register. It may not be the same thing that Bob will end up getting. I will get some, let me write this in say purple. I'm going to get some classical, I'm going to do some process on this quantum register. It's maybe some, big measurement. But that, I mean, maybe I'll say small measurement. I'll do a small measurement. I'll get a register, and I am going to send this register out to Bob. In addition to that, I'm going to send some random bits to Bob, some completely random bits that both Alice and Bob agree. Okay. Now, if this process can somehow ensure the same classical quantum state ensemble as in here, then that means I can say that it is only these bits of randomness that is dependent on the quantum state, and these bits of randomness, the red bits of randomness, are completely independent of the quantum state. So you see what is happening. I make some process on the quantum state. It may be a measurement, it may be a small measurement, and I will get these purple register, and I will send these purple register to Bob. In addition to this purple register, Alice and Bob agree on some complete randomness, some external source of randomness. See, I need randomness to generate this, right? What amount of randomness should come from something related to the quantum state, and what amount of this randomness should come something completely unrelated, can come from something unrelated to the quantum state. If I can somehow simulate this, so previously, if I just did the left side world, right? If I did the left side world, then I had to send h of 0.3, 0.7, so many bits to Bob. But suppose I can reduce that to something lesser. That means in generating this ensemble, the amount of randomness that depends on the quantum state is only the information content of the purple register, and the amount of randomness that's required from external source is this minus the purple register. Do you agree?
Yeah.
Yeah.
That's exactly what I will try to do. So what I will do is the following, and now I'll
Sorry, just one question. Sorry.
Yeah.
So Alice's purple register is not in the system which you wrote above, which was summation theta k tensor k, right?
Yes, it is not in this. You mean this one, right?
Where had you written that system? Yeah.
This one. This is the original system. This is the original system.
No, like yesterday you had this summation of like at the end of everything, we want to end up in this system 0.3 gamma 0 tensor 0
Correct.
plus 0.7 gamma 1 tensor 1.
Correct.
So this system does not contain the purple register at all.
No, this system doesn't contain the purple register.
Okay.
Because,
only the
this is so there is something. So what has happened is the purple register has been traced out. Nature is doing something, getting the purple register, then concatenating it with the red external randomness and getting the the real register, and then the purple register she is not giving you.
Okay, so the system basically is just the state which is with Alice and Bob's register. There is no purple register.
Correct.
It's been traced.
Yeah, and the purple register is really depending on the quantum state. So it's like this, right? So what nature could be doing is nature has this quantum state. She is pulling out something, only looking. She's only going to look at the quantum state, and she's going to pull something very, very informative content. Okay. Then she will add to this some red register, and then she will get out the real register that you are seeing. Okay. This is how nature may be working. So nature, looking at the quantum state, pulling out something very informative and the purple register. Then she will add something completely random, because you're seeing a lot of randomness. We don't know where that randomness is coming. So she adds something completely random, the red register, that is completely outside the quantum state, not even looking at the quantum state. When she adds the two, I mean, adds in whatever sense, right? I mean, she kind of, uses them and creates something. And then she will really give you the register. Okay. This register still has connection with the quantum state, because the purple register came from the quantum state. And you can't completely, unless the red register is so overwhelmingly random, the relationship will be maintained. So if Bob, so what you have to do, Bob has to be only given this, and then nature is tracing out the purple register. She's just throwing it away. She's not giving it to you. Now we are trying to look inside and see, okay, can I simulate this purple register? And can I add this external source of randomness to stimulate exactly what the nature is doing? So that way I know that really the information content of the outcome is really in the purple register, and this red thing is obfuscating the outcome, right? So that gives me a better window into my quantum state. Do you agree?
Yeah.
This is exactly what we will do. So now I'll tell you what is the simulation protocol, and you will get a sense. Okay. So given a quantum state rho, take any quantum state rho, take a measurement lambda k. Okay, what I will do is the following. I will create a bank of measurements. Okay, so I will write this down like this. I'm writing a bank. So every row is a measurement in itself. Okay, every row is a measurement in itself. So I have, say, 100 outcomes. my original measurement lambda has, I was starting with 2 to make it simple. Now I have 100 outcomes. So there are 100 outcomes. This is my original measurement. This is my quantum state rho. I will look at this quantum state and this quantum measurement. And what I will do, I will create a bank of 20 measurements. 20 measurements. So there are 20 rows in this box. Okay. Each fellow, so I will name it, let's say S11, S12, S15, S21, S22, S25, whatever, 15.1, S15.2, S15.5. Okay, I'll tell you how I'm going to simulate this process. I will first ask nature to give me one among 20 random indices. So the nature is going to give me one among 20 random indices. Okay. Bob also has all these outcomes. So he's got 2 registers with him. One register has so he has 2 registers. I'm gonna write it as maybe purple register. So this can be 1 to 5. It can be 1 to 5. And then he's got a red register, 1 to 20. Okay. Now, nature will give them a completely random index from 1 to 20. Okay. Today, nature will wake up. I mean, you're not even looking at the quantum state. You're not even looking at the quantum state. Nature will give the index 13 to both Alice and Bob. Alice, what she'll do, she'll go into her bank of measurement. She'll go to the 13th measurement and she will perform that measurement. Forget lambda, just forget lambda. She will perform this 13th measurement on rho. She will get 1 among 5 outcomes, right? So she may get 4. Right? This is the purple kind of, it's purple. So she gets the outcome 4. She will send this 4 to Bob. Okay, Bob has got 4 with him and has got 13 with him. Somehow he will do something and he will get some number out, 87. That is, and the row will also end up, you will observe that the row will also would have ended up in the quantum state corresponding to the outcome to 87. So I'll call it theta 87. I'll call it gamma 87 because I used to call it gamma. So this is the protocol. So the index to the bank is completely random. Once you get that index, you make the corresponding measurement, and you get an outcome. You say, so what is nature doing? Nature is mixing some measurements. So really, the information content is only in 1 among 5 values. It's not in 1 among 100 values. So this is what is the protocol you will see. And it turns out this number 5 will be an information quantity. It will be S of rho. I mean, the number 5 will be S of rho minus. It will be actually so I'm going to look at this. So I'm going to tell you what that, and then you can kind of maybe stare at it later. So consider this classical quantum ensemble. So I'll call this theta xy. So it turns out that 5, the number 5, right, happens to be I of x colon y with everything measured with respect to the state theta, and 20, which happens to be h of x given y. S of x given y or h of x given y, whatever you want to write the volume one entropy. And if I add this, Suppose I add 5 and 20. So what am I adding? I'm adding x colon y theta. Well, I made a mistake. It's y given x. Okay. If I add these two, I get S of y, which is exactly the entropy of that classical register. So in other words, this is the information content of the quantum state. This is pure randomness. And this is actually the entropy of the post of the classical register that nature is giving you at the end. Does this, I mean, are the calculations looking same? I mean, you might, I mean, you have to maybe view this once more to kind of understand this better, but is this, if you have any questions or doubts that you left at some point, let me know. I will explain.
So,
Can you just
like,
for that, what we said like few minutes back, that right, I of xy correspond to something, s of y given x corresponds to something.
Yeah. So wait, what's your question? Yeah, five,
I
right?
didn't hear it.
Five. Yeah, five. Five means the number of outcomes in each measurement of your bank. Okay. That corresponds to I of x colon y. The number of measurements, that is the amount of randomness that you are seeing, that is completely extrinsic to the state. Okay, so maybe let me explain this. See, when I do the measurement theta, so remember when I have a state rho and I make a measurement. So I told you I'm going to get 0.3 probability sigma rho naught, sorry, gamma naught with the classical register 00 plus 0.7 gamma 1 with the classical register 11, right? You agree with this?
Yes.
Okay. Now I'm going to write this specifically when I have a measurement lambda k. Okay. What is the post measurement? So I have a lambda k. So lambda k runs in k belonging to k. So I have lambda 1, lambda 2. This is my measurement. So I get the when I get the outcome k. So let's think of k. I get this with probability what? Trace lambda k rho. What is the post measurement quantum state when I get k? It's going to be root lambda k rho root lambda k divided by trace lambda k rho. If you are confused, just remember our previous mk rho mk dagger. This was our measurement, and I would get this quantum state when I get the outcome k. All that I'm now doing is just assume mk equal to mk dagger. That's all. Just assume that it is self-adjoint. So then you just say lambda. So then lambda k is mk square, or which is mk dagger mk. So then root lambda k is just mk. So that's why if you put mk here and mk dagger, I mean, they're essentially the same. So just to again, just to cut short this detour. So suppose you may observe outcome k, you're observing that with probability lambda k rho. In that case, the quantum state is this. Okay. So what is the post measurement classical quantum state when I make this measurement? It is the following. You put, remember, I put the probability, I put the quantum state, I put the classical register, right? So what is the probability? Probability is trace lambda k rho. What is the quantum state? It is root lambda k rho root lambda k divided by trace lambda k rho. What is the classical register? It's k. So do you agree that this is the post-measurement quantum state when I make the measurement lambda k on rho?
Yeah.
Okay, great. Srinidhi, is this okay?
yes, sir.
Okay, I am going to call this a big quantum state with two components, x and y. Okay, let's make the following observation. What is theta y? Theta y is the state of the classical register. You will be tracing over the first part. So you're going to trace out the first part. When you trace out, when you do trace on this part will become 1. So I am going to get this. Do you agree? Trace lambda k rho k k. Do you agree?
Yes.
What? So this is a distribution. This is the distribution of your classical register. So if I look at the S of y with respect to the state theta, this is the entropy of your entropy of the randomness in your outcome. Do you agree?
Yes.
Entropy of the randomness in your outcome. Suppose you did not do all this bank, pink, and all that. Suppose you did the original measurement and you wanted to send the classical register to Bob. You needed so many bits of random, so many bits you needed to send. Do you agree?
Yes.
Srinidhi, is this okay?
Yeah. Yes.
Now, remember, I told you, I want to pull out 2 threads. I want to pull out a thread which is really intrinsic to the state and a thread that is extrinsic to the state. So this randomness, total randomness, I want to pull out 2 components, one component that is intrinsic to the state, one component that is extrinsic to the state. So somehow I should write this as a sum of 2 parts, right? That's really what I'm doing. So S of x, I mean I of x colon y with respect to the theta. So what is this? This is really S of y minus S of y given x. Both measured with respect to theta. And so this is this is S of y given x of theta. So many bits of randomness can come from external source, and so many bits of randomness in the measurement outcome has to be communicated to Bob. So this is the information content of the outcome of the quantum measurement, and this is pure randomness that nature is sourcing to generate what you feel is the is the classical register. Do you understand?
Yes.
Yeah.
Yeah.
So that's exactly so we will actually, so what we will do, so that gives us a recipe, right? So what we should do, we should prove that, so now it should be clear what we are looking at. We should prove that there exists a bank with 2 power n S of y given x of theta number of measurements, each measurement with at most 2 power n times I of I of x colon y of theta outcomes, such that if the measurements in this bank are performed uniformly at random. Why? Because nature will give us uniformly at random bits, right? Eventually, uniformly at random, and both the outcome, so uniformly at random, then this simulates the measurement process. Do you agree?
Yeah.
So this is really what we'll do. What we will do is we will design. So we are given rho and we are given lambda k. We will design a bunch of so many measurements. We'll actually design new measurements. We are not. We are going to take the old measurement. We're going to take this measurement, and we're going to take the quantum state, and we're going to design a new bunch of measurements. Each measurement doesn't have so many outcomes as the original measurement. Okay, it doesn't have. So it's like you have the scale. The scale has 100 readings. You're going to create 5 scales with each 20 readings only, and you're going to pick one at random, and you're going to perform that. You're going to use that scale, whatever reading you're giving, that you give that, and that's enough. So not just the classical register, but the entire quantum classical register after doing this bank process, right? So you're first pulling something out, pulling some measurement out at random, and after that you're performing that measurement. So then you will end up with a quantum state, right? This quantum state is a post quantum state of a choice of measurement and performing the measurement. That quantum state will be exactly like what nature is leaving you with, which means that leaves you with the question: is really nature doing this, or is nature really doing what we are doing, right?
Yeah.
So that's, and if your classical register is in the same state as it was if nature was, if you had done the original measurement, then how much ever information content was there in the original outcome should be there in this also. But now you are sourcing some randomness from completely outside, so which means that cannot be information content of the, that cannot be intrinsic to the state, it has to be extrinsic to the state. Do you agree?
Yeah.
That's it. That's the, if you so what I'll do is, I'm not going to I want you to kind of think through this a little bit, understand this. I will do one more I will do one more nice setting, which also it'll be very interesting. Okay, so okay, this is the quantum part, and the quantum part, it requires a lot of kind of like little bit understand. So a little bit history. So finally, people have come to the conclusion that this is really, when you have a measurement, when you take a measurement lambda k, and you take a quantum state rho, the information content in the outcome is only this, though your classical register has so much amount of randomness. The information content is only the green part, and the yellow part is useless. It's useless. But the amount of randomness you're seeing in your classical register is this. Isn't this really? I mean, don't you realize this is really fundamental in the sense that because this is really the window into the quantum measurement, right? So in some sense, this is it's really amazing if you kind of think of it, because you're stripping out. See, it's like this, right? You prepare this quantum, you can't see it. No, I mean, you have no clue. The only window to our quantum state is the measurement. So only if your quantum state, so how does it work? It's like this, right? So you have a machine, you have a big, so let me kind of just indicate how this, I mean, why. So you have a big machine, okay? It has one lever, and it can be put into some 4 position. What you do, you put it in say one position, okay? And you pull out a quantum state, okay? and you make you make some measurement on it. You get some outcome. Great. Then you pull one more copy of this. You keep the register in the same thing. You pull one more copy, make some more measurements. That's how you kind of validate what you've prepared. There is no other way to validate what you've prepared. So you make, you take one lambda, you make, 1,000 measurements, and you see, okay, what is the statistical outcome? You take another measurement, you take gamma, you make thousand repetitions of gamma, you will get some statistics on the outcome. And you put the, you hope that your machine is not going to, misfunction. So after trying this for a lot of time, you realize, okay, this is what is the quantum state. So next time you have a quantum, you put this in this lever, you kind of know what is the statistical outcome. There is no other way to tell what a quantum state is, because randomness in the outcome is intrinsic to the quantum state, and you can't stare at a quantum state. So you really want to know, how informative are these measurements. You'll have to design these measurements, right? So I think this is a very good, this is a kind of a very fundamental result. Now I'm going to pose a nice, classical analog of this, which is also mind-boggling. It is also mind-boggling. Okay, so I will just describe a complete classical counterpart of this problem, and you will be surprised even that is mind-boggling. And I'll tell you the solution to that problem, and that will give you an indication to the quantum result. So think of the following. Suppose I have two registers X and Y. Okay? And I have a distribution Pxy. Okay. Alice is sitting here. She has one register with her. Okay. And nature is putting putting a value into that register with the distribution Px, that is the marginal of Pxy. Okay. Bob is sitting at a different place. He's got an empty register. What you want Bob to populate his register such that whatever Alice sees, which is random, and whatever Bob puts into his register, they resemble the distribution Pxy. You see what I'm saying? So I want a process by which maybe Alice sends something to Bob, or maybe Bob gets something from outside. I don't know, but nature is only putting into Alice's register a random variable with distribution X. Somehow Bob has to pull out the Y, so that X and Y look according to the distribution Pxy. Do you get the problem?
Yeah.
So
Yeah.
One approach, what Pxy is known to everybody. Okay, Pxy is known to everybody. Xy Pxy is known to everybody. Alice is sitting on this side. Bob is sitting on this side. See, if Bob simply pulls out a random variable with distribution Py, it is not going to help, because this is going to be independent of this. Yes, this marginal will be Px, this marginal will be Py, but if somebody looks at the joint joint values that they generated, it's not going to look according to Pxy. Do you agree?
Yeah.
Yeah.
What should Alice send to Bob so that he pulls out Y according to, as though it looks like Pxy? What should Alice send to Bob? See, Bob is not interested in X. Bob is not interested in X. That's a different problem. This is a different problem. Bob is not interested in X. Bob is interested in pulling out a Y as though to simulate nature. So if nature had put X and Y together into Alice and Bob's register, they wouldn't have worried. But now nature is cutting off the link to Bob, and you want to kind of simulate what nature would be giving. Again, it's random. So how much information should Alice send to Bob so that he can end up pulling out a y, so that if there is a universal person who's looking at both x and y, it's as though nature has put x and y into Alice and Bob's register. Do you get the problem?
Like if Alice sends small x, then because Bob knows pxy, he can simulate p of y given x.
Exactly. Srinidhi, is that clear to you?
Yes, sir.
So they're just saying, okay, just send the entire x to Bob, and Bob will, just use whichever that x is. He will pull out a y according to x, and he will simulate, and he will pull out a y, and clearly it will look like pxy, no doubt about it. Well, there is another simpler strategy. Why should Alice send x to Bob? Alice can do this herself and send y to Bob.
Yeah.
That's also okay, right? How much do they need? So first case.
Sorry. Can you repeat that second thing?
Second thing is, why should Alice send x to Bob? Alice can generate the y and send the y to Bob.
Okay, from her x, she generates which y?
She generates a y just like what Bob would have done. Right?
Okay, got it. Okay.
Generates the y and then she sends that to Bob.
Yeah, correct.
So the first strategy of sending x will require h of x bits. The second strategy of sending y will require h of y bits. Okay. Question is, can you do better? Can you somehow come up with a process that you can do better? Now, what I suggest, look at the typical sets. Okay, look at the typical sets of x and y. And then you will get an idea and you will actually get an answer. So think about this. And it turns out this problem is very closely related to the quantum state. It's exactly the classical analog, because remember, Alice performs the measurement. She has got the post-measurement quantum state. She wants Bob to have the corresponding classical register, right? So it has a very similar feel. Actually, yeah, you will get exactly the same answer. So I want you to think of it using, now this is slightly more easier to think because of the typical set phenomena. So I want you to kind of think through this. I will have the next class on Friday, and on Friday I will just give you the sense for this approach, and then I will solve the measurement compression. But now I'll just maybe take some questions or doubts. And if you want to guess the answer to this, I mean, the guess should be simple. But how, if you kind of realize how it's like astonishing. Okay, let me. I will have a class on Friday. Okay, I'll send out an email.
I have a question.
Yeah.
But from the paper, but not about this class. Maybe I'll wait for Srinidhi to ask question, then I will ask.
Yeah, sure. Srinidhi, you have any doubts or it's okay?
Yeah, like I have.
1 second, let me stop recording.